Whenever you have a KP question or the KC question or all equilibrium constants, the only thing that changes the value of KP, that's the change in temperature. That's it. So the answer for this is going to be D. If you change temperature, the value of KP and KC it's going to change. So then you have, okay, let's try and hopefully we hadn't done this question. Let's try and do this question. Let's try and figure out the value of Kp. They're saying that it's 2NO2 and that's reacting. It's in equilibrium with N2O4. And you have to give the expression and you have to figure out the moles of Kp, everything. So initially they're saying that 2 moles of dinitrogen tetraoxide. Which one is this? These are your initial moles. Dinitrogen means two nitrogens. So that's this molecule over here. So initially this was sealed in a container. So there is no NO2, 0 moles of it. So that's your initial moles. And then he's saying that that the total pressure was given, and the mixture of gases contained 1.84 moles of dinitrogen tetroxide at equilibrium. So at equilibrium, you have 1.84 moles of this. So that's your equilibrium moles. We need to figure out the moles of this thing. Okay, those are the moles that need to be figured out. Now to figure that out, what you need is Assalamu alaikum. To figure that out, what you need to know is that you added 2 moles. Now you're left with 1.84 moles. That means 0.16 are missing. That means 0.16 are gone. They've reacted. So they reacted and they probably produced this NO2. So it's if 0.16 are reacting, then on this side 0.32 are going to be produced. So so what would be your equilibrium moles? Your equilibrium moles are going to be they're going to be you had no moles, now you have 0.32 moles getting produced. So at equilibrium, you're going to have 0.32. So we figured out our equilibrium moles, and then he's saying calculate the total number of moles of gas present at equilibrium, hence the mole fraction of each gas. So what's the mole fraction of this? It's 1.84 divided by the total. That's the mole fraction. What's the total moles? It's 1.84 plus 0.32. So if you do that, what do you get? 1.84 divided by what's 1.84 plus 0.32? That's 2.16. And this one is going to be 0.32 divided by the total moles, which is going to be 2.16 as well. One second. So this one is going to be 2.16 as well. Acha, is this clear?
Yes.
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 And at the end, he's calculating the partial pressure. How do you calculate the partial pressure? Multiply the mole fraction by the total pressure, which is 140 kilopascals. It was given over here. Okay, at equilibrium, it's 140 kilopascals, which is mentioned over here. So into 140, that's your partial pressure because of NO2, and this would be multiplied by 140 as well, and that's kilopascals. So you figure out the mole, not the mole fraction, but the partial pressure of the two gases. And the final part is he's asking you to calculate the value of Kp, which we're going to do over there. So it's going to be N2O4 divided by the NO2 squared concentration. So Kp is 140K multiplied by 1.84, and that's going to be divided by 2.16, and the whole thing is going to be divided by 140K again into 0.32 and divided by 2.16. But the bottom one is going to be squared because over here the concentration is 2. 1 second. So the concentration over here is 2. I mean the moles are 2. So the reactant is going to be squared. TK, is this clear? Ethan, Mohammed, is this? So TK. Next one, let me leave this.
Sir,
Yes.
what is the units for KP?
Every time it has to be different. I mean, for example, if you're talking about this question, right? Like this one is about the Haber process, right? So if you're dealing in pascals, the units are going to be in pascals. Like the Kp for the Haber process is going to be the partial pressure of NH3 squared, and it's going to be divided by the partial pressure of N2 multiplied by the partial pressure of H2, and that's going to be cubed. So if you try and use the units over here, it's Pascal, so it's going to be Pascal squared divided by Pascals multiplied by Pascals cubed, and that's going to give you Pascals minus 2. But then sometimes in the question, they won't be using Pascals. They would be using, like in the previous question, the one that we just did over here, they were actually using kilopascals. So when they asked for the unit, which I think they did not actually ask for the unit in this question, but if they were going to ask the unit for this, I mean, what's the expression? It's going to be the partial pressure of N2O4 divided by the partial pressure of NO2, and that's going to be squared, right? So the unit is going to you keep that in kilopascals. It's going to be kilopascals divided by kilopascal squared, and you're going to get kilopascals to the power -1. So Ethan, whatever the pressure has 3 units, it's either pascals, kilopascals, or atmospheres. No need to convert them. If the question is dealing in kilopascals, just keep kilopascals. If it's dealing in pascals, keep the thing in pascals. And the same if it's dealing in atmospheres, keep everything in atmospheres. Is that clear, Ethan?
Yep.
So now the last type of question that I wanted to do was that if the value of either KP or KC is given, I just wanted to find if there was any tough question on this. 1 second. Just wait 1 second. Let me try and. There was actually one question which was. It's probably not in this worksheet. Actually, the last type of question that I wanted to do was the reverse type, which was that the value of Kc would be provided, which. So this is the question that we have. It can be applied to Kc and Kp both. So let me find that question. Okay, so the last type of question is that you might be given the value of Kc, and this could also be applied to Kp, the same thing. The initial moles are provided as are given over here, but the equilibrium moles are not given. So you don't have any idea what are the moles at equilibrium of any one of them. But what they've done is that they've given you the value of Kc, which is probably they're talking about 1200 kelvins, and it's given over here. It's 1.44. So that is already provided. So what you're going to do is that you're going to assume values now because you don't have any equilibrium moles. You don't have anything to work with. So what you're going to assume is because you don't know how much is getting reacted. I mean, the initial moles are given, but you have no idea how many moles are getting reacted or produced. So just assume that X moles, I mean, you added zero point 0.5 moles, just assume that X got reacted. Okay, we don't know how many took part in the reaction. There must have been some forward reaction or there might have been some backward reaction. We have no idea what's going on. So I'm just assuming that X moles are taking part in the reaction. So what are you left with? You're left with 0.5 minus X. I mean, initially you had zero point 0.5, now X have taken part in the reaction. So X moles have taken part in the reaction, so you're left with 0.5 minus X. This one, if X moles of this react, it's 1:1. So it's X moles of H2 would also react. So this one is also going to be 0.5 minus X. And if X moles are reacting, then on the other side, it's 1:1. So X moles would be produced. And X moles of this would also be produced. So that means you had 0.2 moles. Now you have X moles extra that have been produced. So it's going to be 0.2 plus X. And this one would also be 0.2 plus X. So the whole equilibrium moles are in terms of X, ठीक है? Idwa, is this clear? Abha, is this clear? Rida?
Yes.
Achha, so you have 0.5 minus X, 0.5 minus X, and this is 0.2 plus X and 0.2 plus X. Uh, and you can write the expression for Kc. It's products over reactants. All of them are 1 mole, so it would be 0.2 plus X multiplied by 0.2 plus X. All the powers are going to be 1 because the coefficient is 1. And divide by 0.5 minus X. What you can simply write 0.5 minus X into 0.5 minus X. So that's squared. You can also call this squared and get rid of this other thing. So that's your expression, and the value was 1.44. This should come out to be 1.44. Now what you can do is you can underroot the whole thing, get rid of the square. You can be careful with the calculation that you do. You can get rid of the square. If you get rid of the square, what's 1 point? I'm just going to keep it as 1.44 under root. Remember, this would become 0.2 plus X. I mean, the square term is going to get cancelled out. And it would be 1.44. It's going to be 1.44 under root. Just sorry, 1 second, I lost. Somebody's mic is on. I said, let me just find the question. I lost the question. You raised the question just a second. So I found the question. I said you have to be very careful with the calculation. I was saying get this on the other side, so it's going to be zero point 0.5 minus x, right? And you can open up the terms. It's going to be 0.2 plus x, and it's going to be 1.44 under root into zero point 0.5, and then it's 1.44 under root into x. Uh, if you take x as common, it's going to be 1 plus 1.44 under root. The other side would be 1.44 under root multiplied by zero point 0.5 and minus zero point 0.2. Okay, I've taken the zero point 0.2 to the other side, so that's 1.44 under root into zero point 0.5 minus zero point 0.2. And I've taken x to the other side, so that's x plus 1.44x. So that's this thing. And then you, what you do is you divide. So it's going to be 1 plus 1.44 under root. Now be careful with this under root. Remember, under root is going to give you two values. One of them is going to be plus and the other one is going to be minus. So when you're trying to do this under root, you're going to get two values. One is plus and the other one is minus. Okay? Always you get two values. So that would lead to two values for x. So what's under root 1.44? That gives me 1.2, I think. So I have two values. One is plus, the other one is minus. So I need to solve the expression twice. One with plus 1.2. So it's going to be 1.2 times 0.5 and it's going to be minus 0.2 and the whole thing would be divided by 1 plus 1.2. So that gives me one value of x. And the other value of x would be minus 1.2 multiplied by 0.5 minus 0.2 and the whole thing is going to be divided by 1 plus, not plus, but minus 1.2. So can anyone solve and give me the two values of x? And is this clear? Can remember, whenever you're doing this under root, you're going to get two values. One is plus, the other one is minus. Okay, Ethan Mohammed, is this clear?
Yes.
So did anyone solve this? What are you getting? Ethan, are you trying to solve this?
Yeah.
I think I got 2 over 11, 11 over 5.
No, which one? What do you get for
2
that?
over 11 for the first one.
Okay, and if you, what would do? It's 0.188, right?
Yes.
Let's call it 0.189. And what's this one?
I got 11 over 5.
And that's
2,
2.2.
2.2. Yeah.
I said now x has two values. One is 1.8.189, the other one is 2.2. What you're going to do now is only one of them is the correct value. Make sure that the equilibrium moles they can never be negative. I mean, negative moles, they don't make any sense. You either have no moles, that's zero, or you have something. Uh, there is no such thing as negative moles. So which value would you put? If you use 2.2, what's going to happen is that zero point 0.5 minus 2.2 is going to give you a negative value for moles. which is not possible because moles can never be negative. They can't be less than 0. So 0.189 is going to be the correct one, not this one. So you're going to put 0.189. And remember, the question doesn't end over here. Most people actually leave at this point. I mean, they think the question is over because the question was specifically asking for the equilibrium moles. He's saying calculate the amount in moles of each substance present in the equilibrium mixture. So basically, at the end of the day, you have to solve this thing. What are your equilibrium moles? So take 0.189. This would be 0.5 minus 0.189. And this would be 0.2. And all of them is good. So you have to actually solve this, and that's going to be your answer. Okay? Is this clear? Okay. Zaib, is this clear? I said let's try and solve another question similar to this. And remember, you can get a similar question for KP as well. Acha, 1 second, let me try and find. So this one, he's saying that these are the initial moles, and I think he did not give you any equilibrium moles. What's given is the value of Kc, which must be given in the previous part. That Kc is 140 and 59 at 650. So I think he was talking about 650. So the Kc value is given over here. At 650 Kelvins, it's 59. So you know the Kc value, and you have no idea what the equilibrium moles are. No information is provided. And what you're going to do is you're going to figure out, you're going to assume that X reacted. So it's 1:1. So if X of H2 reacted, then X moles of I2 would also react. And on the other side, 2X would be produced. So that's our assumption. So equilibrium moles are that it's 0.02 minus X because you're assuming that X moles have reacted. And over here as well, it's going to be 0.02 minus X, and on the other side, it's going to be 2X because there was no moles of HI, and now you have 2X moles getting produced. So, so X moles reacted, X moles of this reacted to produce 2X moles of that. And then you're going to just use the Kc expression. The Kc expression is going to be HI concentration product over reactants. So HI concentration would be squared and divided by the H2 concentration and I2 concentration, and that's going to be, they're going to have power 1. So it's going to be 2x squared divided by 0.02 minus x into 0.02 minus x. I mean, these are the reactants. So that's going to be squared as well, and the value is 59. So again, be careful with the calculation. You have to solve this. And the same thing would be done. You're going to just take the under root. So it's going to be, the squares would get cancelled out because of the under root. It's going to be 2x. And your 59 under root would be multiplied by 0.02. One second, I've lost the question again. I think it's this one. So it's going to be 59 under root multiplied by 0.02 and also 59 under root multiplied by x. So this multiplied with this thing, and then you solve for x. X would come out to be, if you take x common, it's going to come out to be 2 plus 59 under root. And on the other side, it's going to be multiplied by 59 under root times 0.02. And you can solve for x. It's going to be 2 plus 59 under root. And again, be careful that it's going to give you two values, because 59 under root is going to have two completely different values. If you take under root of 59, you get either 7.68 plus or 7.68 minus. So there would be two expressions. One would be for plus 7.68 times 0.02, or the other one is going to be minus 7.68. So can anyone try and calculate what the values are?
Sir, for the first one, I'm getting 0.016 mole.
Take a 0.
0.16.
Three significant figures here.
159.
ठीक है, so 0.0159. And for the second one,
0.0270.
so 0.270. I hope I've actually done the working correctly. So it's 0.0159 and 0.0270. There's actually 0.0159 and 0.0270. 0.0270 is not going to work, because if you put 0.0270 over here, this value over here is going to come out to be negative. You can't have negative moles. So that means this one is the incorrect value. This is the value that you're going to use, which is 0.0159. That's the value that has to be used. So that's 0.0159 is going to be used, and you have to make sure at the end of the day, find those equilibrium moles. Okay? A lot of people, this is very common, they just find the value of x and they just leave the question over there. Uh, the equilibrium moles, they need to be found out. Achha, then you have, so most of the questions are pretty similar. What we can do now is, we've pretty much done all the KCKP questions, all types of KCKP questions. What we can do now is, we can do reaction kinetics. Okay, that is something that we haven't yet done. Okay, just 1 second. So we can do reaction kinetics, which is a very small chapter. That's so what happens in reaction kinetics? The first thing is we need to revise what you've done in O levels. So we're going to quickly try and do that. Now, reaction kinetics is most of it is in A2. You're going to study the chapter in A2. What you're going to study is the first thing is what are the 5 factors that a rate of reaction depends on. Basically, whenever there's a reaction happening, there are particles that are colliding with each other. So let's say there are red particles and there are blue particles over here. Why do they need to collide in the first place? So that old bonds can be broken. For example, you have N2 molecules. So that's a very strong triple bond. And on the other side, you have an H2 molecule. So collisions, they need to happen. And when the particles collide, the old bonds would be broken and new bonds are formed. So it all depends. The reaction speed, etc., depends on the collisions. So that you can break the old bonds and then new bonds can be formed. So which is why whenever there is a reaction, you can't have two solids in a reaction. The particles, one of the particles at least has to be moving so that it could do the collisions. Okay, that's very obvious. So it's either a solid with a liquid or solid with a gas or two aqueous things or two. It just can't be two solids reacting with each other. That's not possible. Um, Now, when something collides, collisions can be described in two ways. One is how many times do they collide? So there's a thing called frequency of collisions. So how many times are they colliding with each other? And the other one is the effectiveness of the collisions, or how forceful are the collisions, whether the collisions are successful or not. I mean, why were they colliding with each other? So that they can break each other's bonds, right? So so one is the frequency, the number of times they're colliding, and the other thing is effectiveness. Now, if you increase any one of them, the rate of the reaction would speed up. If you increase both of them, then the rate of reaction would obviously speed up. Uh, so so every time you're going to describe, whenever you're going to describe collisions, you're going to comment on these two things. One is the frequency, how many times they collide, and how vigorously are they going to collide with each other. Now, the first factor is temperature. That would affect the rate of the reaction. And it effectively doubles the rate of reaction for every 10 degrees centigrade rise in temperature. So that's the first factor. And we know that what does temperature do? It increases the kinetic energy of the particles. So can anyone tell me what would happen? Will the frequency of collisions increase or will the effectiveness of collisions increase?
Effectiveness.
Both, sir.
Both of them would increase because the particles would be more energetic, so they would be traveling much faster. So they would be bumping into each other a lot more. So the frequency of collisions would increase. Plus, they would be more energetic, so there would be a lot more forceful collisions that would be happening. So both in this case, both frequency and the effectiveness of collisions increase. And then you have point number two, which is what's the other factor?
Pressure.
The other factor is pressure. Pressure is will it affect the rate of the reaction if it's a solid or a liquid or an aqueous solution?
No.
Okay, so pressure is only for gases because only they are compressible. Uh, so when you have a container and you increase the pressure, what you're basically doing is you're compressing it. So when you compress something, the particles would become closer together, especially because gases are the only things that are really compressible. So when you compress, you're pushing it down, right? So the particles become closer together. So when you have higher pressure, and remember these small points are very important. A lot of people are very bad at expressing this. I mean, they obviously know, but you have to use the correct terminologies, okay, when you're answering questions. So particles are closer together. So what happens? Effectiveness or the frequency of collisions?
Frequency.
Okay, so it's only the frequency because the particles are not energetic, so they're still bumping into each other with the same force. The only thing is they're closer together, so more frequent collisions. You get a lot more frequent collisions only, not effectiveness. That pretty much remains the same. So what's number three? That is going to affect rate.
Catalyst.
Okay, so that's a catalyst. What does a catalyst do?
It lowers the activation energy by providing an alternate reaction pathway.
Okay, so it lowers the activation energy, right? Uh, and what that means is that what does lowering activation energy means? I mean, what does it do? For example, if you have this reaction happening, like this nitrogen molecule and this H2 molecule are reacting together, why is this reaction so difficult? I mean, what's the problem with this reaction? Why don't they just bump into each other and they react?
Because the triple bond of nitrogen needs a lot of energy to break, high bond energy.
Okay, so that is basically activation energy. You need because the bonds are very strong. If the bonds are very strong, they're not going to break easily, and they have to bump into each other with a lot of force, which is why they have to be very energetic. So that's your activation energy. So lowering activation energy means they somehow make it easier to break bonds. To break the old bonds. They kind of make it easier to break the old bonds. And there are two types of catalysts. One is a heterogeneous catalyst. So there is a thing called the heterogeneous catalyst, which is the reactants and the catalysts have a different state. They have different. So, for example, in the same reaction, you have N triple bond N. It's about to bump into a hydrogen molecule. Now, the problem is they need a lot of energy. Otherwise, the triple bond is not going to break. And you add an iron catalyst. Let's say this is the surface of the iron catalyst. Transition metals are very good catalyst, and they're very good heterogeneous catalyst. The state is different. The reactants are gaseous, whereas the iron is solid. So does anyone know how does iron actually make it easier for these two molecules to break the old bonds? What does the iron do?
Is
Any?
It
that
provides
from
Hmm?
form like weak bonds.
Exactly. So what the iron does is it does a thing called adsorption. Uh, it adsorbs reactant molecules. And let me explain what that means and why are transition metals such good catalysts. Uh, Transition metals are unreactive metals. Basically, the reason they are unreactive metals is they have a lot of protons. They don't like to lose electrons. They actually tend to attract electrons. Like gold is or platinum, it's very unreactive because it doesn't like to lose electrons. They have this non-metallic tendency of actually uh, metals like to lose electrons. Transition metals are the word transition. The reason the word transition is used is because they are somewhere in the middle of a metal and a non-metal. Like a gold atom doesn't like to lose electrons. A platinum atom doesn't like to lose electrons. In fact, they have this weak attraction for electrons. But they're not like non-metals. Non-metals attract electrons very strongly. Like Cl would tend to gain electrons and become -1. Transition metals are attracting their own electrons very strongly, so they don't lose electrons like group one metals. ठीक है, but if potassium is in the same row as iron, potassium has 19 protons, so it loses electrons a lot easier. It's a lot easier for potassium to lose electrons. For iron, because it has a higher number of protons, doesn't really like to lose electrons. So iron is very unreactive, not as unreactive as gold, but it's for example, rusting of iron takes years. I mean, it takes hundreds of years for iron to actually rust completely. So what it does is it sees the triple bond, it sees all these electrons, and it starts pulling on those electrons. That's adsorption. It sees electrons in the bond over here. It starts to weakly, not like a non-metal. A non-metal would strongly attract the electrons. A transition metal would very weakly attract electrons. And what that would do is that the electrons in the triple bond would eventually they're going to get pulled towards the iron catalyst. So the electrons were previously being shared by the two nitrogen atoms, but what the iron did was that it slightly started pulling the electrons towards itself, very weakly, not very strongly. And as a result, the triple bond weakened. And so it's not going to completely break. I've completely broken it just to show what iron is doing. It's not going to completely break, but it's going to get weakened. Like if it was a triple bond, then maybe electrons from one of the pi bonds might get pulled towards iron. So now you're just left with the double bond that's going to break, or maybe the two pi bonds, all those electrons might get attracted to the iron, and they would be adsorbed on the surface. Okay, is this clear?
Yes, sir.
So now it's a lot easier to when these two would collide, it would be a lot easier to break the bonds because now there is no triple bond because the pi electron cloud, the electron density above and below, that's getting attracted to iron. Okay, is this clear, Minail? Is this clear?
Yes, sir.
Okay, and plus the other thing is that this adsorption is very weak. So it's not like the N would get stuck with the iron. The N could, if it's energetic, could fly off in any direction whenever it wants. So iron is not like a non-metal that it would strongly pull the electrons and keep it with itself. So the attraction or there's going to be just a slight pull towards iron, and that would weaken the bonds. So that's how the activation energy gets reduced, and that's what a heterogeneous catalyst does. So you have these transition metal catalysts. Uh, why are group one metals such bad catalysts? Because group one metals they don't actually like to gain electrons. They're always losing electrons. Why are non-metals such bad catalysts? Because if it was a non-metal, for example, over here, if it was chlorine, chlorine would simply pull the electrons and keep it with itself. It's not going to let it go. So transition metals are kind of in the middle. Just a very slight tendency to pull the electrons. So just a very slight pull towards iron, and that would weaken the bond. And when these two collide, that would make it a lot easier to break the bonds. So that is what a transition metal does. That's known as adsorption, uh, and that's what a heterogeneous catalyst is. We're going to cover the rest tomorrow then. Okay? Homogeneous catalyst and the rest. Okay? Any questions about this? Clear है?
Sir, I have a question.
Yes.
When we discuss the pressure factor, if when I'm answering the question and I mention that it increases successful collisions, would it be wrong? You said it only affects frequency, not the successful collision.
Basically,
Like
basically the
because
term, basically it's going to be wrong. Basically, it's the percentage of effective collisions, or the effectiveness of collisions is not affected.
okay,
It's going to be wrong. Uh, Remember when you the percentage of effective collisions or the effectiveness of the collisions, you're not making them more energetic. So they're going to collide in pretty much the same way. It's just that they're now more frequent. Okay, so this is the factor. It's going to be marked wrong.
okay,
Okay, you
okay,
either
sir.
write effectiveness or the successfulness of the collisions. Those two terms are usually used. चलिए ठीक है.
Okay, sir. Thank you,
Okay,
Professor.
take care. Allah Hafiz.
Sir,
Yes.
for Kc and Kp values, Kp is for gases only, right? So what is what Kc?
KP is for gases only, and KC is for KC is for concentration. I mean, when you use the term concentration for which substances, you use it for aqueous solutions, and you also use it for gases as well. But normally, you don't use it for gases.
Okay.
But
Okay. Thank.
but you can use concentration can be used for gases as well. For solids, Kc is I mean the concentration is constant. It's taken as one. And I told you that if anything is in excess, like in aqueous solutions, water would be taken as one.
Yes. For if Kp and it's a solid, do we write 1 or 0?
No, you write one, because if you write zero, the whole expression gets cancelled out.
Oh,
The pressure of a solid is not going to change. I mean, for gases, the pressure would change. So
okay.
if you have a Kp expression, the partial pressure for gases is only going to be taken. For anything that's aqueous or liquid or a solid, that's going to be taken as one constant.
So we don't include it.
Yeah, I mean it's going to be taken as one, not zero. TK, it's going to be taken as one. So that basically means you're not writing it in the expression.
Okay.
Okay then. Take care.
So, thank you.
Any other question? चलिए ठीक है. That's it. Allah Hafiz.
Allah Hafiz, sir.